So 4.4 is our strategy for when we see two terms. There are two other categories of polynomials that have two terms. They're in our textbook, but we are not going to cover them. So they're in the next section or in the next level of math in the Math 50 course. We're just going to talk about difference of squares. So we're first going to start talking about what happens when you square numbers. And so if you were to square a number, we come up with this list, this really awesome list that are perfect squares. Because if we were to take this list, you can take the square root of these and go back to this number. So that idea that the square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4. And so we have this, not 14, we have this relationship between these perfect squares and these numbers. And so we're going to use this list as something to reference when we're starting to talk about what do we do when there's two terms. So overall, how to recognize a difference of squares is we're looking for a perfect square first term, a perfect square second term, and they're separated by a minus sign. It's a difference of squares, so that means minus. This is the general form for it. So this would be a perfect square, and this is a perfect square, and there's a minus sign in between. And so when you take the square root of this, or sorry, when you factor this, you end up with this. If you remember in chapter 3, this was a special pattern. And the whole reason that that's in chapter 3 as a special pattern was for you to recognize this in reverse in chapter 4. So in chapter 3, this is what we talked about. So you had the exact same two things in the brackets, but you had a positive and a minus. And the pattern that we were to recognize is that the middle term disappeared. But in this, when I taught it, I said you can always FOIL it out. So you can always FOIL it out. Oh, first outside, so negative AB, inside, positive AB, negative b squared. So you can see here, the middle terms are going to cancel out. So you're left with this a squared minus b squared. So again, with these ones, you know, going this way was chapter 3, and going the reverse, going backwards, is chapter 4. So this would be a perfect square. So we've got numbers that are perfect squares, and we're also going to talk about what makes variables perfect squares. So these are numbers that are perfect squares. What about variables that are perfect squares? What we're looking for are even exponents. So variables look for even exponents because they are perfect squares. You can take the square root of those. We're going to move through these examples and identify, are they perfect squares or not? And if they are perfect squares, we're going to practice taking the square root of them. And so what we're looking for in perfect squares are either a number from this list, because we can take the square root of it, and variables that have even exponents. So for A, 36 is great because it's in this list. We could take the square root of 36 and get 6. But the x, we can't take the square root of it, so it is not a perfect square. If I were to take a look at B, B is also not a perfect square. The 24 is not in this list over here, and so it is not a perfect square. The 6, the x to the 6 is totally good because that's an even exponent, but the whole package has to be a perfect square. So C, if I take a look at C, I have a 9, and that's cool because it's in my list over here, and it has an x to the 4th. And that is awesome because I can take the square root of that. So that is a perfect square. If I were to take the square root of 9x to the 4th, I'm saying what times itself would equal the 9x to the 4th. You can use your calculator to take the square root of a number. So that's a 3. And if you were to take the square root of x to the 4th, saying what times itself would give you 4x's, well, that would be x squared. Okay, let's move on through a few more of these so you can see what is a perfect square, what isn't, and if it is a perfect square, how do you take the square root of it? So D, first off, it has a number 64, and number 64 is over here in this really awesome list, so that makes the number part of it, the coefficient part of it, a perfect square. The second part of it is an even exponent. So we have x to the 6. 6 is an even number, so this is a perfect square. So let's practice taking the square root of it. Whoops, I copied it wrong. So we have the square root. Come on, erase. Oh, there it goes. So the square root would be of 64, x to the 6, would be 8x, and then it would be x cubed. You're dividing the exponent by 2 in order to take the square root. And so what we're saying here is 8x cubed times 8x cubed is 64x to the 6th. Okay, a few more. Let's keep going. So E, we've got 16x to the 9. So 16 is great because it's 4 squared. So that coefficient is a perfect square. But the variable part of it has x to the 9. And I can't divide 9 by 2. And so that makes this not a perfect square. F, 36x to the 12. So 36 is in that list, and 12 is an even number, so that makes this a perfect square. So taking the square root of it, taking this example one step further, the square root of 36 is 6, and the square root of x to the 12 is x to the 6th. Another one, 4x to the 6. So 4 is in the list up here. That's 2 squared, so that's cool. And we've got an even exponent on the x, so it makes it a perfect square. So if it is a perfect square, we should be able to take the square root of it. Square root of 4 is 2, and the square root of x to the 6 is x to the 3. H, 9 is a great coefficient, but we've got a 7 on the x, and because it's not an even number, it's not a perfect square. 24, I, 24 is not a perfect square because 24 is not a perfect square coefficient. And J is a perfect square. The square root of 16x squared is 4x. So practicing recognizing a perfect square and taking the square root of that perfect square is absolutely a key step in this next kind of factoring. So these ones we want to just practice recognizing. So we're not going to factor these ones, but we want to recognize if they are a perfect square or not and what we're looking for there. So 81, x to the 4th is good. 36, y to the 6th, that's cool because that's a perfect square. And we have a minus sign between. So those are the 3 things we're looking for. It is a perfect square. For B, I've got 9, great. X cubed, as soon as we see an even number here, that is a problem. That's not a perfect square. And so that disqualifies this from being a perfect square polynomial. We can't factor it with our understanding of a difference of squares. C, we've got 36x to the 4th, which is good. We've got 16z squared, which is good. But the third thing to check, this is not a difference of squares. This is a sum of squares, and that is not going to fit our pattern here. The last one, so we've got 36x squared, y squared. Lots going on, but that's a perfect square. We've got 9x to the 4th, y to the 6th. Again, lots going on, but it is a perfect square. And we've got a minus sign in between. So that is a difference of squares. So these are our instructions. We always want to look for greatest common factor first. We want to recognize if it's a difference of squares. So those are 3 things to check: a perfect square, and a minus in between. We're going to draw 2 brackets. We're going to put a positive sign in one and a negative sign in the other. And then we're going to take the square root of the first term and write it the first place in each bracket. Then we're going to take the square root of the second term and write it in the second place in each bracket. So let's try this. So first, A, we've got x squared and minus 16. So perfect square, minus sign, so it fits. We slap down two brackets. One bracket's going to get a positive, one bracket's going to get a negative, and these brackets should be identical if we fit our pattern, right? So square root of the first term would be an x. Square root of the second term would be a 4, and we're done. In this one, you could always check it. And for one of these, I think it's worth checking. So we could FOIL it out. And this was the case where that middle term went away. And we should be back to our original question. So let's try these ones on the page here. We've got a few to go through. I think I've got them all on the page. Yeah. Okay. So first off, we need to recognize how they are a difference of squares. So we've got a perfect square, and a minus sign. So we slap down our brackets. One gets to be positive, one gets to be negative. The square root of 4a squared is 2a, and that goes in the first place of each bracket. And the square root of 9 is 3, and that goes in the second place of each bracket. You could always check these by FOILing them back out, but if we followed our pattern correctly, that should be our answer. For D, I recognize, is it a perfect square, or is it a difference of squares? So I have a perfect square, and a minus sign. So I can put down the two brackets. One bracket gets to be positive, one gets to be negative. In the first location, I take the square root of the first term. So 9 square root would be 3, and the square root of b squared is b. And so 3b goes in the first location of each of my brackets. And then the square root of 25 is 5. And so that goes in the second location in both of my brackets. Difference of squares is maybe my favorite kind of factoring in the course. It's almost unnerving because it's fairly simple. You know, the lines of the long cut, the lines of work you had to show in all the other factoring, this one's way simpler. And so sometimes people get a little nervous. F, we have a perfect square, and a minus sign in between. So I can put down the two brackets. One set of brackets get to be positive, one set of brackets get to be negative. And now I'm going to take the square root of the first term. That would be a 7c squared, and that goes in both places. And then the square root of the second term, so that would be a 3d in both places. If you're ever nervous, you can always check, but that should be the factored form of that polynomial. A few more down here at the bottom, they start to get a little weird. This one still fits the pattern of difference of squares. Now we have a lot in these brackets that are squared, but it's still something squared, and a minus sign in between. So we're going to make my brackets a little bigger. And I find this one to be a lot easier if I show people how it goes. So one brackets get to be positive, one brackets get to be negative. And honestly, the second term in here is a whole lot easier to do than the first term. So we'd have 13 in both places. Remember, when we're taking the square root of something, we're saying what times itself gives me what I'm after. So here, this is literally x minus 5 times itself. We don't even have to do any thinking because it showed me it's squared, right? So I write it like that. And this fits the pattern, but we're not done. We need to simplify this. So we can drop our brackets in both and collect up our like terms. So my final answer for this one would be a little weird and a little harder to check, but technically this is my simplified answer. H is somewhat like that. So once you've seen one of these, remember how it fits the pattern. Perfect square, minus sign. And again, that 81 is undoubtedly easier to take the square root of. The first term, you just really write what's in the brackets because it's as if that work hadn't been done yet. And in order to give your final answer here, we want to drop the brackets and gather our like terms. So I'd get an x plus 2 and an x minus 16 as my answer. For the last two on the page, we've got this case that we need to remember. And so we really need to remember that we look at greatest common factor first and then on to how many terms. So we talked about 4 terms, we talked about 3 terms. Now we're talking about 2 terms, but it's always greatest common factor first. So when I take a look at J, I don't see a difference of squares. If I take a look at greatest common factor first, I could pull a 2y out of each of these terms. If I pulled a 2y out of each one, I would in the brackets then have 16x squared minus 9y squared. And I've made a difference of squares. So the 2y I want to be part of my answer, but the other part is a difference of squares. So you push down the bracket or put down the brackets, you take the square root of the first term and the square root of the second term, and you should be done. And again with this one, if you wanted to, you could reverse it back out. You could FOIL out your 2 binomials and then distribute the 2y, and you should end up back to your original question. K is another one for you to give a try with. Take a look at the greatest common factor first and see if you can uncover a difference of squares. I see that I've got a 2a common to both, and factoring that out would give me a 25a squared and a minus 4b squared. So the 2a is still going to be part of my answer. The rest of this is a difference of squares. And that would be my polynomial in factored form. I've added 2 more to the notes on the top of the next page, and then I'm going to cut the video because the next bit is just bonus. It's not tested. It's in Math 50 only, but I will make a little video explaining it. How about these ones? So these are the sneaky ones. A would be a difference of squares. If you remember back to that list, 1 is a perfect square. Take 1 and take the square root of it in your calculator. You'll get 1. So this is a difference of squares, but it's tricky to recognize, and so that's why I put it in here. We'd have x in the first place and 1 in the second place. And again with this one, if you don't believe your calculator, if you don't recognize the pattern, you get this answer. You could always reverse it back to the original question with FOIL to check. Okay, B. Take a look at it. I see it as a difference of squares. But I'm not done. Take a look at the second binomial there. That second binomial is actually another difference of squares. So we have to keep going on this one. I'd still have this 4x to the fourth plus y squared, but this one is going to break apart again into the difference of squares. So 2 more binomials. So the square root of the first term and square root of the second term. And you're not done until things are fully factored. A bit of a sneaker one there for sure.